Wow. Okay. Slowly but surely, there it is. Go full screen. We're picking up on example 4 on 5.1. We're solving separable differential equations. We got general solutions, and then we have particular solutions. All right, so example 4, for each of the following, find the general solution, which is y equals f of x, by algebraically manipulating the differential equation into a separable form. Okay, so again, if you have in general dy dx equals f of x times g of y, the separation would look like this. You got dy equals f of x times g of y dx, but then you have a function of y on the right, so you would have to divide through by it. So 1 over g of y dy would equal f of x dx. Okay, so you're not going to be asked again to solve a separable differential equation if it's not one that can't be solved. So dy dx equals, we have e to the x minus y. The first thing that you could always do is to multiply both sides by dx, because that's going to get rid of it from the left and bring it to the right. And so then if you're going to accumulate your x's on the right, you're going to want to accumulate your y's and dy's on the left. But I have a y on the right that's trapped right now in an exponent. Any idea how to free it from the exponent? Say what? Natural log, both sides. Natural log of dy equals the natural log of the whole thing. Well, I could expand that and say it's plus the natural log of dx. It's worth a try, because that's going to give you now x minus y plus the natural log of dx. And then I add a y to the other side. So I have y plus the natural log of dy equals x plus the natural log of dx. Okay, that did separate the variables, but it's not in any kind of integrable form. The integrable form is going to be the integral of f of x dx. That's the integrable form. So how would we get it back in integrable form? We'd have to now we have the dy and dx trapped. We'd have to e both sides, and that won't work. It'll kind of get us back to where we start. So that was nice that you thought about that. But the technique's a little bit easier. It's what we did yesterday. You could split it up, right? E to the x times e to the negative y. Yeah. And that makes it now a factor that has y in, and now you can just divide both sides by that factor, and you get 1 over e to the negative y dy equals e to the x dx. Now that is the separation you're looking for. Now on the left-hand side, notice you could bring the y to the top, or the e to the y to the top, and make its exponent positive, and you get something that looks like this, which is a little bit easier maybe for integration purposes. All right, so once you show the separation, you get the check, then you're going to integrate both sides. And now they're both in integrable form. So what becomes of the left side? The antiderivative e to the y with respect to y? E to the y. Do we need a plus c on that side? No. They're going to be collected on the right. The antiderivative of e to the x is e to the x plus c. That would earn a check probably for both antiderivatives, a single check for both, and then a plus c gets the check. All right, now we need to solve for y. So Colton, how do we now unexponentiate it on the left?
Colton south, by the way.
Colton south. That's right. You natural log it. So you don't really have to show that step. If you know the natural log of e to the y is going to be y, it's going to be the natural log of e to the x plus c. Notice the plus c now moved from the outside, which was a vertical shift, now to the inside of the argument, which is more of like a horizontal shift. It is inside the argument. Did we solve for y? Yeah, there it is. That is your general solution. And that's it. It didn't ask us to find any particular solution, so we're done. So that would probably get another check. So notice that would be worth 1, 2, 3, 4 checks probably. If you have an initial condition, you're going to get another check for using it and writing the particular solution. Here's how they're scoring this, though, on free response questions. The separation of variables, of course, is the first check. And then everything else after that, you're going to get up to 5 more checks after that. But if you do not show the separation of variables, but you somehow manage to get everything else after that without showing the separation, like in your mind you just jump to the antiderivatives, you get 0 points if you don't show the separation of variables. So it's one of those almost like punitive measures where you're not even eligible for anything if you don't show the separation of variables. So it's 1 point for showing it. It's up to -6 for not showing it. So the moral of that story is to show it. Yeah, show it. All right, let's look at this one over here. This one kind of looks funky. dy dx minus x equals xy squared. What's up with that one? You want to multiply both sides by dx first? I would have to distribute it. Yeah, I would add x first. If you think of the dy dx as being kind of like an x that's in algebra 1 that you're trying to solve for so that you get it by itself, you would want to add the x to both sides probably first. And you get positive x plus xy squared. Now if you multiply both sides by dx, that wouldn't be bad, but here's what you have to be careful about. Could you just do it like that? No, it would have to be in parentheses. Is that the separation we want? I still have a y on the right. How do I get the y from the right to the left? Factor out, there you go. The only way that you're going to be able to separate variables once you have your dy dx on either side is by multiplying or dividing. Adding and subtracting is not going to work. So you're going to have to factor out the x, and that leaves you a 1 plus y squared. Now remember, constants can be on either side as long as the x and y's are separated. By factoring out the x, I have a single representative x, and then I have a factor that only has y's in it. That's the key to a problem like that. Factoring out and then dividing through by the whole quantity that I highlighted, you'll have 1 over 1 plus y squared dy equals x dx. Good job, James South. Factoring out. That show the separation? Yes. Oh, it's James West. I see what we're doing. We're switching. No, because that would give you away. We don't want to do that. No. All right. So now that we've separated the variables, we integrate and we integrate. It goes in the front on both sides. You can't just like put an integral at the back there like that. That doesn't work. Okay. All right. So let's see the left side. The integral of that with respect to y. It does look familiar. What is it? That's arctangent of y. Don't need a plus c on the dependent variable side. And x, that looks familiar. 1/2 x squared plus c. For a problem like this, where the antiderivatives are dramatically different on either side, as opposed to the previous one where they were both the same rule, really, you can earn really a check for each antiderivative and one for the c. So you can earn another check there. Now I just need to solve for y. How do we inverse or arctangent something? Tangent it, right? So tangent of arctangent of y becomes y. You don't have to show that. And then you get tangent of 1/2 x squared plus c. Notice c now moved inside the angle. And again, you're not multiplying both sides by tangent, so you can't just put like parentheses and put tan at the back. That's kind of funny. We will take away points as we laugh. All right, there you go. You solve for y. There is the general solution. And if you had an initial condition in order pair, you could plug it in and find the value of c. C is now inside the angle. So when we take the antiderivative, that plus c gets added on immediately. And before this section, every time we've done that, it's been a function of x on the right. It's always manifested itself as just a vertical shift, right? But notice for these types, because our integral or derivative equation has x's and y's, what starts off as a plus c, which might be a vertical shift, by the nature of solving for y, that c gets absorbed into a different place. And it could end up being, either a, if we come back up here, it could either be like a vertical dilation factor, right? Vertical dilation factor. It could become a horizontal shift, as in that case there. It could be, I guess, on the inside there, another horizontal shift. What else? I guess these are both kind of horizontal shifts as well. So it's not always just going to be a graph that is vertically shifted. These C's can move around and affect the general solutions in several different ways. And if you look at the original picture that we had, those are all the particular solutions. You can kind of think of all of them together as being representative of the general solutions. Those aren't just vertical shifts of each other. So the C there kind of affected the graphs in a different way. That's kind of a segue into the next section. All right, example 5. So far, so good, by the way? So good so far? For the differential equation, are we missing a symbol? We're missing a symbol. We're missing a symbol. You want to do minus?
Yeah.
Okay. Gosh dang it. We haven't had that problem in a while. You want to do minus? Let's do minus. For the differential equation, y dy dx minus x equals 0, find the general solution equation. The general solution equation means that we have to what, that equation? Separate it and solve it, right. And solving, remember, means getting back to y equals. So the first thing we have to do is separate the variables. So if we agree it's a minus sign, we get y dy dx. If you add x to the other side, you get x, positive x. And then you divide through by y, or you leave y over there. Let's leave y over there. Yeah. We'll get y dy equals x dx. There would be the check for the separation. Integrating both sides. Integrating. We get the integral, and now we have 1/2 y squared equals 1/2 x squared. That was where you would earn just one check because they're so similar, and then plus c would earn the other check. So very similar to what we did the other day, or yesterday, I guess. Bless you. Multiply everything through by 2, and you get y squared equals. When you distribute, you get an x squared plus 2c, but 2c becomes new and improved ShamWow c. Because we're in the process of solving for y, we can still let c absorb things. We're not in our locked-in general solution yet. Now, when I solve for y, I do have to consider plus or minus for the general solution. And as we saw yesterday, there's really no way in this type of problem, like there was for the natural log, to bring the c out front to absorb the plus or minus. So that would be our general solution with the plus and minus intact. Now it says to find the particular solutions that pass through the point 0, 4, 4, 0, and 0, 0. Huh? Oh, that should be negative 4. Thank you. Yeah. There is a space. Good. Good catch. All right, let's do A first. 0, comma 4. So you could say like at 0, comma 4. We just basically take the general equation, plug in our 4 for y. Plus or minus, we get the square root of 0 plus c is c. When you square both sides, you get 16 equals, plus or minus becomes positive 1, really, when you square it, and you're left with c equals 16. So the particular solution is y equals, leave a little space, square root of x squared plus 16 under the radical. And then for a problem like this, you do have to commit on your particular solution to plus or minus, and you don't want to guess, even though the odds are decent, right? How do you know if it's plus or minus? Well, just try out your initial condition. When you plug in a 0, you need to get out what type of 4? A positive 4. So the only way to do that is if there's a positive sign in front. So that right there would be the solution. If you already left the space and you don't need to put a plus sign there, just leave it, or I guess erase it and do it again if you're doing it on paper, or put a big plus sign there. Would that be a good thing? I don't know. I don't know. I don't know if I'd put a plus sign there. It looks like a T. Okay. Part B. What if we are now using negative 4, 0? So at negative 4, 0, we would plug in. We would get 0 for y equals plus or minus negative 4 squared is 16 plus c. If I square both sides, I get 0 equals 16 plus c. So c would equal negative 16. So y would equal plus or minus the square root of, going back to the general form, x squared minus 16. Now, is it going to be plus or minus? Minus? It could be minus, actually. Because if you notice here, when I plug in a negative 4 squared is 16, minus 16 is 0. It doesn't matter if there's a plus or minus there. This function, the only difference between the plus or minus is whether the graph opens up or opens down. But if you're on the x-axis, they would share that point in common. So this one would have two solutions. It doesn't matter if you use plus or minus on this one. Let's throw a bonus question in there. Let's call this, I guess I'm labeling them wrong. It's supposed to be II and II, but oh well. Let's call this one C and just be cavalier. What if we wanted 0, negative 4? Well, now if we plug into the general form, we would get negative 4 equals plus or minus the square root of 0 squared plus C. Square both sides, you get 16 equals C. So y would equal, leave a little space, the square root of x squared plus 16, which is the same one we got on A. But now, because I need to plug in a 0 and get out a negative 4, this is where you would have to commit to the negative in front of the radical. And you have to do that on your own accord. Particular solutions can have plus or minus in front. And I'm thinking in hindsight that that's maybe what I intended to ask on part B. So now we have it. All right, part D. I. We're passing through 0, 0. And we'll say then 0 equals plus or minus the square root of C. Square both sides, you get C equals 0. So y equals square root of x squared. Is it plus or minus out front? Does it matter? No. So we'll leave it as plus. And of course, if you take the square root of x squared, you get y equals x, right? And it's the same domain because notice this allows all values of x. So does that. Because you're squaring it first. So that's kind of similar to what we saw in the opening with the onion bulb, where it turns into a straight line. Oh, the absolute value of x. Yeah. I'm sorry. I was I was talking about the domain, and I made a point in my mind to bring it up, but I didn't execute it. It would be the absolute value of x. Thank you. It would be the absolute value of x. Because anything that comes out of there is going to be positive, right? What if I... Yeah, the square root of x squared is the absolute value, yeah. But could it also be negative? Let's have a little discussion here. If I chose the negative version, would it still pass to the point 0, 0? It would. So if I left the negative intact there, it could also be y equals negative absolute value of x. Yeah, so it would be that or that opening down. Well, let me draw it a little bit better. It would be that opening up, or it would be that opening down, which means it could either be plus or minus absolute value of x, because they share the vertex at the origin, or it could be the line y equals x and the line y equals negative x. It could handle both of them. So, yeah, either one. Again, the general solution when it's at the origin could be any one of those. Depending on whether you're, up here at another point on the graph or down here, then you can probably get more information about where you actually are. And when we get into the next section with slope fields, you're going to see intersection patterns like that. What this is probably going to do, the general solutions for this probably end up being a family of hyperbolas. That's what the C more than likely does, okay? And these right here would become lines or the slant asymptotes. So if you happen to be anywhere along those lines, the general solution, the particular solution itself is a line. But anywhere else in the coordinate plane, it ends up being one branch of a hyperbola. Bless you. So the next section is slope fields, and that's going to give us kind of a nice visual of what all the family of particular solutions look like. Law of exponential change. This is kind of a nice little subcategory for differential equations. This is one of two important rules for growth that you need to memorize and just kind of be able to go to the general solution without having to separate variables. For an exponential growth function, the more you have, the more you get. So we've talked about exponential growth in pre-cal. People sometimes say things grow exponentially and they haven't really done the quantitative analysis to support that claim. They just mean it grows really, really fast, right? But true exponential growth is quantitatively exponential. The more you have, the more you get, right? You have $1 in the bank and you're earning 5% interest a year. You come back a year later and how much do you have? $1 and 5% of $1, which is 5 cents. So you have $1 and a nickel. But if you put $100 in the bank and you come back at 5%, you have now $5. Okay, so you earn more money. The more you have, the more you get. Okay, that's the true quantitative description of exponential growth. The more you have, the more you get. Exponential decay, the more you have, the more you lose, or the less you have, the less you lose, if you want to look at it that way. So we can actually say that like this. The rate of change of the quantity, that is how fast it grows or how fast it decays, is directly proportional to the quantity itself. The more you have, the more you get, because the faster it grows. The less you have, the less you get. The quantity grows at a rate that's directly proportional to the quantity itself. You can write that like this. If you let y equal the quantity, then the rate of change of y with respect to time, how fast y is growing or changing, is directly proportional to y. Okay, we write direct proportions as like linear functions. Some constant, which I'm calling k, times the quantity y. So notice what the direct proportion means. If y gets bigger, dy dt gets bigger. If dy dt gets bigger, y gets bigger, and vice versa. They have the same behavior. If one gets bigger, the other gets bigger. If one gets smaller, the other one gets smaller. And they're related by way of some constant k. Okay? So the more you have, the bigger y is, the more you get, because the faster it's going to grow. Now, let's go ahead and solve that separable differential equation. To separate the variables, I would have dy equals k times y times dt. Now, I need to get all my y's and dy's on the left and all my t's and dt's on the right. And any constant, in this case k, your constant of proportionality, it could stay on either side. It doesn't really matter. Typically, if you can, if it doesn't make the problem too ugly, you can leave your constants on the right, because that's where they're going to end up anyway. So let's divide through by y, and you get 1 over y dy equals k dt, where k is a constant, so that's the separation. We got it. All right, now we integrate both sides. And what's the antiderivative of 1 over y with respect to y? Natural log, absolute value of y. Good, we don't need the plus c. And then k is a constant, so the antiderivative of k with respect to t would just be kt plus c. Now, we've seen this before. To unnatural log, we e both sides. So we're going to get the absolute value of y equals e to the quantity kt plus cth power. And as we saw in the example yesterday, that's that cantilevered exponent. It's kind of gross. We don't want to leave it like that. So I'm not going to drop the absolute values yet. I don't want to put the plus or minus in front. It's too much labor. So I'm just going to call that e to the kt times e to the c, just like yesterday. And because we're still in the process of finding the general solution, I can still let c absorb things. So e, the number e, raised to the unknown number c, becomes yet another unknown number by which we are multiplying, and so we can bring it out front. And with it out front now, when we drop the absolute values, as we saw yesterday, we do not need the plus or minus in front of the c, because c takes care of that for us. So that is the prettiest general solution to the differential equation, dy dt equals k times y. If and only if. Now we can make it a theorem. So that's the thing. You don't have to reinvent the wheel now every time it's going to be an exponential growth or decay problem. As long as you recognize it's exponential growth, you can jump right to the general solution, which is y equals sect. We call it the sect equation. Okay? C is your initial value, because it corresponds to t equals 0. It's your y-intercept of the graph. E is, of course, 2.718. It's exponential growth. K is your constant of proportionality. Now notice if k is a negative number, what is that going to do to your graph of E, which is growth? If your independent variable has a negative in front of it, it's going to reflect it across the y-axis, which now makes it decay. So whether it's growth or decay, whether something's doubling or tripling or halving, you're going to be able to write every single exponential growth or decay function essentially in terms of base e. Now there are other bases that might be more useful, but you can always write them in terms of e. All right, so how are you going to recognize that it's exponential? Well, if you ever are told that dy dt equals k times y, you know it's going to be the sect equation. Or if it says something like the weight of a newborn baby gorilla increases at a rate that is directly proportional to its current weight, you'd be like, oh, baby gorilla, what else did you say? That's cute. What do baby gorillas look like? Baby gorilla. Where's the baby gorilla? There's a baby gorilla. Oh, look, day 0. Oh, day 0. Look, day 8. Oh. Let's go back. All right. Hey, let's try it out. Let's try it out with a warm-up. A cute little baby gorilla's fur during the first 8 days of its life, the fur itself, grows at a rate that is proportional to its current length. Ding, 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 right? The more fur it has, the more fur it gets, right? It grows at a rate proportional to its current length. That's the key wording for an exponential growth. So what we could do then is we could say y equals c e to the kt, where y is going to be the fur length, okay, and t is the time in days, where t has to be between 0 and 8. Sweet. Now, it says if its fur is 1 inch long at birth and 3 inches long on day 5, how long is it on day 8? Well, let's see. In order to use this equation, we have to have two pieces of information because we have to find c and k, right? Do we have two pieces of information? Yeah, on day 1, it's 3 inches. On day 5, it's 8 inches. So we have these two ordered pairs. We have the time, which is birth. That would be time equals what? Yeah, we could say assume that's 0, and it's 1 inch long. And then 5 days later, it's 3 inches long. And we want to know how long is it on day 8. Now, here's what's cool about the sect equation. Whenever you have an ordered pair, 0, comma, whatever, that y value is your what? It's your c value right there. And if you're not sure, you could actually just plug it in. Plug in the 0.01. You could say at 0.01. You get 1 equals c. E to the 0 times k is 0. E to the 0 is 1. You get c equals 1. So that means your equation now can be bolstered up. Instead of sect, it's 1 times e to the kt. You're building the equation. Now, you wouldn't have to show that work. If you have the y-intercept, if you have the true initial condition, that is the one that corresponds with t equals 0, then the y value there is your c value. But you could do it that way as well. Now we could use the point at 5, 3, and we'll do the same thing into our most recent version, which is down here. So now we get 3 equals 1, which we don't even have to show really, e to the 3k, and now I have to solve for k. How do I solve for k? ln, anyone? ln both sides? Natural log of 3 equals the natural log of e to the blob, which is the blob. So k would equal natural log of 3 over 3, or 1/3 natural log of 3. There's your k. Now, sometimes multiple choice questions just ask you to find the value of k. And that would be an answer choice, of course. If that's not an answer choice, it could be the natural log of what? We bring the 1/3 up. Cube root of 3, they like to play with logs. So that right there, in and of itself, makes a great multiple choice question. But what we want to do is write our model. So our final equation is y equals 1 times e to the kt, which I'm just going to leave it as 1/3 natural log of 3 times t. And now we have a function so we can use it to evaluate the baby gorilla's fur length at any value of time between 0 and 8, and we want to know what it is at 8. So y of 8, that is the fur length in inches at day 8, is e to the, and if we plug in an 8 for t, we get 8/3 natural log of 3 inches. And of course, if you wanted to see what that was, you can go to the calculator and type it in. Or maybe we can simplify it a little bit, huh? What could I do with that 8/3? I could bring it up as an exponent on the 3. And now what's e to the natural log of blob? The blob. So it's 3 to the 8/3 inches. Yeah, sorry. Got to really work on the levels there. Which could be the cube root of 3 to the 8th power, something like that. So it makes it a little bit easier to maybe calculate. Maybe also a way to disguise the answer on a non-calculator portion of an exam. Now notice if we could do it with our final answer, we could do something similar with your equation. And here's the other thing. As I said already, every single exponential growth or decay function can be written in terms of base e. Okay, because the k in the sect equation is going to not only make it growth or decay, depending if it's positive or negative, but because it could be bigger than 1 or less than 1, whatever it is, it can appropriately horizontally stretch or compress, which kind of makes it any degree you want. So once you set it up in the sect equation, if you have to use it repeatedly, you could actually simplify the equation like we did the number down here. Now you'd have to do a little bit of manipulating here. You'd have to bring the t over with the 1/3 and call it e to the t/3 times the natural log of 3. And now you could bring the t/3 up and call it e to the natural log of 3 to the t/3 power. And now e to the natural log of blob is blob. So this is a maybe more convenient way to maybe not write the equation. Sometimes we can get information that we can write the equation directly like that, but at least if we wanted to use it repeatedly, we could do that. Now, we did this a lot in pre-cal last year. The description for something like this would be like if the baby gorilla's fur triples every 3 days in size. This is what you could go directly to. Because if something triples, a reasonable base is 3, and if it triples every 3 days, remember you would just modify your exponent by doing t divided by whatever that quantity is. All right? So once you had this, if you needed to go backwards to the e version, you would have to go up. You'd have to say that that's the same as e to the natural log of blob, and then manipulate it. So just be aware of that. You can write any exponential function as base e, but sometimes it's a little bit easier for actually using it to write it in terms of some simplified base. All right, so anyway, there it is on day 0, and you can see it's definitely longer. Already needs a haircut, or at least a stylist. Speaking of stylists, I quit using styluses because they just break too often. You know, my finger has not broken yet. And you always have your finger with you. Hey, that reminds me of a joke with fingers and monkeys. Yeah, you know the joke, right? Why are monkeys' nostrils so big? Because their fingers are so big. That's right. Yeah, it is good. I remember that one from when I was little. That's a nose-picking joke. Yep. All right. So memorize. If dy dt equals k times y, then y equals c times e to the kt power. Now the variables might change. There are other versions of sect. C and k are just arbitrary letters that we use to represent the initial value c and the horizontal dilation factor k. I've seen it in this version before. Instead of the sect equation, they call it the naked equation. And I'm like, you don't need to be talking about naked. It's bad enough to be talking about sect, right? No need to be talking about naked. You could also replace c with p, and k with r, and you get what some people call the PERT equation, the shampoo equation, okay? And that is typically what's used instead of y. They usually call it a. This is what's usually used when you're talking about money that is continuously compounded. R would be the rate at which it grows. P is the original amount, the principal amount, and A is the amount at time t. It's all the same equation. They all grow at the same exponential rate. The more you have, the more you get. The less you have, the less you use. Okay? You know what else grows exponentially? Bacteria. A population of bacteria in a culture increased from 400 to 1,600 in 3 hours. Holy moly, smokers. Assuming that the bacteria population P grows according to the rate equation, dPdt equals K times P. There you go. There it is. It's not Y, it's P. But it grows at a rate proportional to itself, where T is the time in hours. Find the value of K. So here's where they force you to use the sect equation, because let's take this problem from a pre-cal perspective. If I just told you to write an equation, you know in 3 hours it went from 400 to 1,600. That's what? Increased by a factor of 4, so quadrupled. So if you were in pre-cal, you might just say, okay, the population P, maybe you talk like that in pre-cal, the population P, let's see, what was the initial population of bacteria? I don't know. I'm going to call it C. And then times, let's see, if it quadrupled, a good base would be 4. And let's see, it would be in how long? 3 hours. Okay, so that would be T, what? Divided by 3. Yeah, go me, pre-cal. And then all you'd have to do is figure out what the initial population was. That would be a decent one to use, 4 to the T-thirds power. But notice, when they tell you that it grows according to this model, and they ask you to find K, is this going to help you do that? Not in that form. Now, you could come in through the secret entrance, okay? So let's do it both ways. You could say C times. Okay, 4, that's the same as E to the natural log of 4 to the T-thirds, right? Now you're just making a ladder, right? It climbs its way up. And then you get C times E. The T-thirds in the exponent can climb out front to the first exponent, becoming T-thirds natural log of 4. Yeah? And now just with a little clever regrouping up there, you could say that it's 1/3 natural log of 4 times T. And now you can get K. K is what? You have it in the sect format, and K must be, 1/3 natural log of 4. That should be an arrow. Yeah, there we go.
Will it always be the time period natural log of whatever factor you drew by?
That's a great question. It looks so. It looks like those numbers, if you replace them with variables, would show up there, right? It would be, let's see, the natural log of 4 because it quadrupled times the time, the reciprocal of the time it took. Yeah, I think that's right. So that's one way to do it. The other way to do it is to say, okay, dPdt equals K times P. I know that's going to be P equals CE to the KT power. And then all you have to do is say, okay, it went from 400 to 600 to 3 hours. So you could actually then, because you're only after K, you could say that, what could we do? We could say that at T equals 0, it was 400. And then 3 hours later, it was 1,600. You'd have to make up that ordered pair. And then you'd have P equals 400 e to the KT. That's your y-intercept. And then you'd use the other ordered pair, and you'd get 1,600 equals now 400 e to the 3k. And then you'd solve. You divide through by 400, and you would get 4 equals e to the 3k. You would take the natural log of both sides, and then you would solve and get k equals 1/3 natural log of 4. Which, again, is the natural log of the quadrupling times the reciprocal of the time it took to do that. And again, as I mentioned, that right there in and of itself makes a good multiple choice question. So that's kind of what forces you to go through the sect version instead of possibly through just setting it up immediately from the description in terms of a more appropriate base. Bless you. How fast is the population of bacteria increasing when the population is 3,000? Notice we don't really know what the initial population was. When I found it using the sect equation, I arbitrarily called 400 associated with 0 because it didn't matter I was after k. Notice on part B, we don't need to know what the initial population is either. It just says how fast is the population increasing when the population is 3,000. How are we going to answer that? We want to know the rate of change of the population, right? So we're looking for dp dt. On part B, we want dp dt when p equals 3,000. Well, I have my equation now up here. dp dt equals k times p. What's k? 1/3 natural log of 4. So it's 1/3 natural log of 4 times p, which is 3,000. So if you simplify, you get 1,000 natural log of 4, which would be the natural log of the 1,000th root of 4. Oh, I don't think so. We don't want to do that. No, it'd be the natural log of 4 to the 1,000th power. Yeah, not the 1,000th root. That makes it smaller. What would be the units on this? That's the exact answer. It would be per hour. Yeah, it's units of P over units of T, so it would be bacteria per hour. So you can answer those two questions right there without even knowing what the initial population is, the actual initial population. Either one of those makes a pretty good multiple choice question. If the second question was the only one that was asked, and the first one never was, you would have to know then to do part A on your own, right, to find the value of k so that you can plug it into your little differential equation right there. Yes, yeah, it would. It would work. Yeah, because over here I just left it as a generic C. Okay, good stuff right there. Exponential growth or decay. Let's look at example 8. We got time for this one, and then maybe we'll pass out the take-home test. An amount A increases at a rate proportional to its current amount. So there's a verbal description. We don't know what the amount is, but we know the more we have, the more we get. That means it's exponential. Such that dA dt equals k times A. Oh, okay, I was thinking that already on my own. You didn't need to tell me that. But I got it. Where t is measured in hours. If the amount triples every 11 hours, find the exact value of k. If the amount triples every 11 hours, find the exact value of k. You have two options. You could do it either way like we did up here. You could set it up using your little pre-calc knowledge and then convert it to base E, or you can go to the sect equation, create ordered pairs. What are y'all more comfortable doing? The what? You like the ordered pairs? Okay. So if the amount triples every 11 hours, so at time equals 0, we don't know what the initial amount was, do we? So we can make something up. 57.6 or 1. And then using the rule, if it triples every 11 hours, then 11 hours later, what's triple 1? 3. Those are arbitrary points. So then you can go right to your solution equation. Instead of y equals sect, it's a equals ce to the kt. And now, since we arbitrarily chose the y-intercept to be 1, we can kind of make that just e to the kt, because c is 1. And now we plug in the other point. So we get 3 equals e to the 11k. Natural log both sides. And divide through. And we get 1/11th natural log of 3, which, as Berquist kind of pointed out, does that fit that little template? Yeah, it does. It tripled. So that's the natural log of 3 every 11 hours times the reciprocal of 11.
Teachers and students, please pardon this interruption.
So that's not a bad way to do it.
Students to take dual credit during the fall semester next year must have completed steps 1 through 6 of the dual credit packet and have turned in all documents to the counseling offices by the end of the day today. Students currently enrolled in dual credit who plan to continue with dual credit next fall must have pages 2 and 3 completed and turned into the counseling office also by the end of the day today.
And at this time, if you could please turn your TVs to channel 4 for the morning announcements, or you can view them on your iPads at vhstv.com.
There you go. So here would be the second way to do it. If you just want to kind of assume the initial value is 1 again, if it triples every 11 hours, you can go straight to the base of 3 because it triples raised to the t divided by 11th power. So that every multiple of 11, 22, 33, you're getting another full tripling factor. That's why that works. And then, of course, you would just use this little trick. E to the natural log of blob is the blob. So that becomes e to the natural log of 3 to the 2 to the 11th, and you got all these layers now. So then the t to the 11th slides out front. Associative property of multiplication. Bring the t to the front, and you get 1/11, so natural log of 3. And now you have you have sect right there, and so the k would be staring at you right there, which is the same thing we got. And then I guess the third way to do it, if you have room in your hard drive, right, you can kind of just look at the pattern and say, okay, it's the natural log of what the population did times the reciprocal of how long it took. Just don't get them backwards, right? No, not necessarily. No. Again, these something like that, if it asks you to find the exact value of k, they make good multiple choice questions. Yeah.
Will they always have to give you the factor at which it grows and the time period? So you could always use that?
Not necessarily. They could give you 2 ordered pairs. Then it becomes a little more interesting. Like at this time, there was this amount, like at t equals 5, there were 100, and at t equals 7, there were 3,000. You want to see what that looks like? That's a little bit harder. It wouldn't be as easy, right. And that's more of a pre-cal problem, in all honesty. What we're trying to communicate here through calculus is somehow relate the equation itself to its rate of change. And that's the path that we're taking in this class. And this differential equation then leads to this type of exponential function, which we've already studied in pre-cal. In pre-cal, we had stuff like if at 2 there's 5, and then at 5 there's 12, write the equation of the form y equals a times b to the x. We did that before, and you actually would plug in, and you'd get b equals a times b squared, and then you get 12 equals a times b to the 5th. And then how would you solve that system? Well, you could divide one by the other. I'm going to call this equation 1 and that equation 2, and I'm going to do 2 divided by 1. So you get 12 over 5 equals, and it works because your a's divide out. A divided by a is gone. B to the 5th divided by b squared is b cubed. And then, of course, you solve for b, and b equals 12/5 to the 1/3 power. And you leave it like that. So once you have that, you can plug this back in to either one of those to find a. And, of course, once you get your equation, you can simplify it. And then if you need to convert it to base e by using e to the natural log of blob, but you're not going to have to do that in this class. That's more of a pre-cal problem. But it's still on the table in terms of the realm of possibility of what actually can take place outside the classroom, like in the real world. Yeah. Oh, will they change that? Yeah. Maybe. Like maybe if the amount triples every hour or every 20 minutes, what's the population at 1 hour? Something like that. It would be something that's relatively nice. Like on y'all's last test, remember we had something like it changed per foot, and then it says what is it at 6 inches or something, and you had to use 1/2 instead of 6, that kind of thing. Yeah. Okay, we'll stop right there. We'll pick up with example 9 tomorrow. We should be able to finish the exponential, or this 5.1 tomorrow. So make sure the worksheet doesn't sneak up on you. We got through example 8 today.